Good evening, everyone. So today we are going to start a new section, method of variation of parameters. If you recall that till now we have seen only one technique, which is method of undetermined coefficient to compute yp, which is particular solution of non-homogeneous differential equation where there is a restriction on r of x, which means the r of x must be sine, cosine, polynomial or exponential function, and there is also restriction on the homogeneous part where p and q are constant. Now if I consider a general second order non-homogeneous differential equation y double dash plus p of x y dash plus q of x y is equal to r of x, then we will see how do we compute yp when yg is known. Yg is known, it means that if we consider the homogeneous equation y double dash plus p of x y dash plus q of x y is equal to 0, then for this homogeneous equation, if we can compute yg, then using yg or using y1 y2 we can compute yp. So we already know many techniques to compute yg, so that's why if yg is known, we will see how do we compute yp. So to compute it, we will use the same logic where we have solved homogeneous differential equation, y1 is known and we have to find y2. To solve it, we use the concept that y1 and y2 are linearly independent, therefore one must be a known constant multiple of the other, which is y2 is equal to v of x y1. Similarly, we know that yp must be linearly independent from y1 and y2, and therefore we assume, so since yp y1 y2 must be li, so we assume yp as v1 of x y1 plus v2 of x y2. Yes, because yp cannot be written as c1 y1 plus c2 y2. So now I must compute v1 and v2 to find yp. To compute v1 and v2, I must, since I know that yp is a particular solution of equation 1, so therefore I must compute yp dash and yp double dash and put it back into the equation 1. So now my yp dash is v1 y1 dash plus v2 y2 dash plus v1 dash y1 plus v2 dash y2. Yes. Now if I compute yp double dash, then there would be a problem. I will have only one equation and I will have v1 and v2, their first derivative and second derivative. So there is no way that I can solve it. It means I cannot compute v1 and v2 by substituting yp dash and yp double dash into the given equation. So now I will put, or I will impose a condition here. So the condition is that assume v1 dash y1 plus v2 dash y2 is equal to 0. If I assume this one, then one thing is that when I compute yp double dash, then there is no derivative of v1 and v2, second order derivative would not be there. The other thing is that I will consider it as one equation, and by substituting yp dash yp double dash into the given equation, I will get another equation that gives me the two equations or a non-homogeneous system of equation which I can solve to have v1 dash and v2 dash, from which I will compute v1 and v2. So if I assume this one, then my yp dash would become v1 y1 dash plus v2 y2 dash, and therefore my yp double dash would be v1 y1 double dash plus v2 y2 double dash plus v1 dash y1 dash plus v2 dash y2 dash. If I put the values of yp dash and yp double dash into the given equation 1, then the equation 1 will become, I am rearranging the terms as well, which you can verify by yourself. So taking all the coefficient of v1, which is y1 double dash plus p y1 dash plus q y1, taking coefficient of v2 common, so y2 double dash plus p y2 dash plus q y2 plus v1 dash y1 dash v2 dash y2 dash is equal to r of x. Now recall that y1 and y2 are the solutions of the homogeneous differential equations. Yes, because yg is c1 y1 plus c2 y2, where y1 y2 are solutions of homogeneous differential equation. Therefore they must satisfy the homogeneous differential equation, and therefore y1 double dash plus p y1 dash plus q y1 is equal to 0, y2 double dash plus p y2 dash plus q y2 is equal to 0. So this gives me v1 dash y1 dash plus v2 dash y2 dash is equal to r of x, and I already have one equation, which is v1 dash y1 plus v2 dash y2 is equal to 0. So this is a non-homogeneous system of equation. Now I just need to check that is this system consistent, or does it has a unique solution, or infinitely, or no solution. So I can write down the system as y1 y2 y1 dash y2 dash, then v1 dash v2 dash, and then 0 and r of x. So this system looks like ax is equal to b, and its solution is x is equal to a inverse b if a is invertible. Yes. So what do you think? Is a invertible or a is not invertible? A is invertible if determinant of a is non-zero. So determinant of y1 y2 y1 dash y2 dash, is it 0? Non-zero. It's non-zero, because y1 y2 are linearly independent, and this is actually the Wronskian of y1 y2. Since y1 y2 are linearly independent, the Wronskian is always non-zero. That's why it's invertible, and this is why my v1 dash v2 dash would be 1 by determinant of a, which is Wronskian, and then y2 dash minus y2 minus y1 dash y1. So this is the inverse of the matrix A, and 0 and r of x. If we solve it, then your v1 dash would be minus r of x y2 by w, and v2 dash is equal to y1 r of x by w. That gives me v1 is equal to integration r y2 by w, and v2 is equal to integration r y1 by w, and that gives me yp is equal to y1 v1 plus y2 v2. Yes. So this is the method of variation of parameter. Now let's see some questions based on this method. So find yp. So find yp for y double dash plus 4y is equal to 10 2x. So for finding the yp, I must solve the homogeneous part first. So my homogeneous part is y double dash plus 4y is equal to 0. That gives me the auxiliary equation, and that gives me yg is c1 cos 2x plus c2 sin 2x. Now I can take cos 2x as y1 or y2, doesn't matter, but I have to remember that which one I am taking as y1 and y2. So if I fix them, then the Wronskian comes out to be cos 2x sin 2x minus 2 sin 2x and cos 2x, which is 2 cos square 2x plus sin square 2x, that is 2. So I have calculated Wronskian. Now recall the formula of v1, which is minus y2 which is sine 2x, r is given as tan 2x, and w is 2. This is dx. I can write it as minus sine square 2x divided by cos 2x dx, and again sine 2x can be written as 1 minus cos square 2x by cos 2x dx, which further can be simplified as minus, sorry, 2 I have missed, so 2 is here, 2 is here, so minus 1 by 2 sec 2x, 1 by cos 2x is sec 2x, and cos cancel out, so cos 2x and dx. Now I know the integration of sec 2x and cos 2x, so minus 1 by 2, integration of sec 2x is log sec 2x plus tan 2x divided by 2, and integration of cos 2x is sin 2x by 2. So this is my v1. Similarly, using the formula, I have to compute v2. So applying the formula is quite easy. The only thing is that you should be good in integration. So this is cos 2x tan 2x by 2 dx, which transformed into integration of sin 2x, because you write tan 2x by cos by sin by cos would cancel out. So this is minus 1 by 4 cos 2x. It means my yp is v1 y1 plus v2 y2, where v1 v2 has already been computed. Yes. So now you must be able to understand the method. So let's try one more question. Please do all the question by yourself first, and you can see that all these questions cannot be solved using the method of undetermined coefficient. So again I must consider the homogeneous part first. So y double dash plus 2y dash plus y is equal to 0. That gives me the auxiliary equation, and that gives me the values of the root. So my yg is c1 plus c2x e raised to the power minus x. So I can consider y1 is e raised to the power minus x, y2 is x e raised to the power minus x. Now compute the Wronskian. So if you compute it, it comes out to be e raised to the power minus 2x, which means my v1 is minus y2r by w, which is minus x log x dx. So now I can consider it as first function, this as second function. So this integration would be minus outside. So integration of x is x square by 2 log x, minus differentiation of log x is 1 by x, integration of x is x square by 2 dx. So this becomes x square by 4, this one, because again you integrate x, minus x square by 2 log x. Similarly you compute v2, which is y1 r by w dx. Here the only thing is that when you wrote w as e raised to the power minus 2x, it cancels out with r of x, because r of x is e raised to the power minus x log x, and y1 is e raised to a minus x. So e raised to a minus 2x would cancel out, and that's why it get into the simplified form. Similarly, v2 comes out to be the integration of log x dx. The integration of log x dx, so what you do is that you take it as 1 dot log x dx, and now you call it first function, this is as the second function. So integration would be log x, integration of 1 is x, minus differentiation of log x 1 by x, integration of 1 is x dx. That gives me x log x minus x. It means my yp is 1 by 2 x square e raised to the power minus x log x minus 3 by 2, which comes because it is v1 y1 plus v2 y. Yes, let's see the last question, very interesting question. So the last question suggests that I must solve x square minus 1 y double dash minus 2xy dash plus 2y is x square minus 1 whole square. Now if you see the homogeneous part, then homogeneous part is not very trivial to find yg. So my homogeneous part is y double dash minus 2x by x square minus 1 2x plus 2 by x square minus 1 y is equal to 0. Now there are two main methods, either transformed into an equation with constant coefficient, where you will see that your z is integration root qx, so root 2 by root x square minus 1, which is integrable. But more easy approach is to identify one solution first. So here p plus qx is equal to 0. See, you can see that 2x square minus 1, 2x square minus 1 is common. It means y1 is equal to x is one solution. And I know that y2 is vy1, where v is equal to 1 by y1 square e raised to the power minus p dx. So now the calculation is quite easy. V is equal to integration 1 by x square e raised to the power minus, and my p is minus 2x. So minus 2x by x square minus 1 dx. Now to integrate it, I can simply take x square minus 1 is equal to t, that gives me 2x dx is equal to dt. So this becomes the integration of 1 by x square e raised to the power integration 1 by t dt, which is integration 1 by x square e raised to the power log t and then dx, which is integration 1 by x square and t, which is x square minus 1 and dx. So now you can see that it transforms into a very easy form. So this would be integration 1 minus 1 by x square dx, which is x plus 1 by x. It means my y2 is vy1, which is x multiplied by x square plus 1 by x, which is x square plus 1. So now you have computed y1 and y2. Now using the method of variation of parameter, I must compute yp. So for yp, the first thing is the Wronskian. I am not going into the detail, but if you compute it, then it comes out to be x square minus 1. v1 is minus ry2 by w dx. If you simplify it, then it turns out to be minus x square plus 1. The other things would cancel out, so it's minus x cube by 3 minus x. Similarly, v2 is ry1 by w dx, which again things would cancel out and turns out to be x square by 2. So if you substitute the value of yp, which is y1 v1 plus y2 v2, it turns out to be. So now again you can see that yp is nowhere easy to guess by inspection. Also you cannot use here the method of undetermined coefficient, because the left hand side here are p and q are not constant. Right hand side is a polynomial, but left hand side must be the equation with constant coefficient, then only you can use the method of undetermined coefficient. So that's all from today's class. In the next class we will discuss operator method.